Hello and welcome back to this course, covering the exam topics for the JNCIS ENT certification. In this section of the course, we're reviewing high availability, what it means, and features to be used to facilitate a highly available network. In this lesson, we'll be reviewing a feature in Junos that allows us to take individual devices which have minimal hardware redundancy built in and combine them into a highly redundant virtual chassis. We'll review the properties, configuration, and monitoring of the virtual chassis feature. So let's get started with reviewing in a bit more detail what exactly a virtual chassis is. Some other vendors have features very similar to the virtual chassis and call it a switch stack or something similar. This is the concept of taking multiple physical device chassis and connecting them so that they act and are managed as a single virtual chassis. This means all of the individual physical devices will be configured from a single management interface. In the case of Juniper EX switches being connected in a virtual chassis, each additional switch will act as a line card or FPC, and therefore interfaces on the other line cards will be referenced using the standard interface naming convention for Junos of using the interface prefix and the FPC number first to reference another line card in the virtual chassis. To create a virtual chassis, the individual physical chassis must be connected using specially designated virtual chassis ports, or VCPs. The EX3400 platform and EX4300 platform switches have built-in QSFP Plus 40 gig interfaces on the rear of the physical chassis that are configured as VCPs by default. Other 10 gig uplink ports may be configured as VCPs as well by the administrator. Now that we have a sense of what a virtual chassis is, let's review some of the properties of a virtual chassis and the formation process. In a virtual chassis, the member switches are identified with an index number. This number can be manually assigned, or will automatically be incremented by 1 for each additional switch that is added as a member to the virtual chassis. The index number begins at 0, with the first switch in the chassis being member 0. This member ID functions as the slot number when applying interface configuration to the switch, or FPC number, where GE interfaces on member 0 would be referenced as GE0XX, and interfaces on member 3 would be referenced as GE3XX. As we mentioned, the member ID can be manually specified. This is called pre-provisioning the member switches in the virtual chassis. This is done using the serial number of the member switch and defining the member ID in the primary RE's configuration. In a virtual chassis, we will also have two REs, RE0 and RE1. If all configuration is left to the defaults, the first switch to power on in the virtual chassis will assume the role of RE0 and member ID 0. And the second switch to power on will assume the role of RE1 with member ID 1. We can have a maximum of 10 switch members in a VC, with member IDs 0 through 9, though by default we will only have 2 REs. In our diagram below, we see an illustration of a common method of interconnecting switches in a VC, and what the default roles and member IDs would be if the switches were powered on in order from top to bottom. Great. Let's now move on to the configuration of a virtual chassis. First, starting with the simplest configuration method, dynamically configured virtual chassis. When setting up a dynamic virtual chassis, no configuration is actually necessary to form the virtual chassis. We would simply connect the VC ports on each switch to the VC and power on the switch intended to be the primary RE first. Once the primary RE is booted, we can power on the intended backup RE next to allow it to take the role dynamically. Finally, once the backup is booted, we can power on the remaining switches to allow them to assume the line card roles. These switches will automatically, dynamically discover one another over the VC ports. Although we can simply connect and power on the switches to form a VC, it's highly recommended to at least explicitly configure the primary and backup REs in the configuration. If the above procedure was followed, the primary and backup REs will have member IDs 0 and 1 respectively. In this case, we can use this command, set virtual chassis member ID, mastership priority, and priority number to set the priority for electing the REs. The highest priority value is 255, and the highest priority value seen will be elected the primary RE, with the second highest being elected the backup. If both are the same priority, the one which was powered on first will assume the primary RE role. Something very important with Virtual Chassis is that all participating switches must be running the same version of Junos to be added to the VC. If there is a switch that is not running the same version, it will show as an inactive member of the VC. It's possible to have the primary RE automatically update the software version of any added switches to the VC to the same version running on the VC to resolve the mismatch. This is done by configuring the set virtual chassis auto SW update command. Finally, to add another standalone switch to an existing virtual chassis, it's as simple as connecting the VC ports and powering on the switch. Of course, the same Junos version requirement stands if the auto SW update configuration is not present. Excellent. Now we've talked a bit about virtual chassis ports, or VCPs. Let's cover those in a bit more detail next. The EX3400 and EX4300 line of switches have built-in VCPs by default. These are QSFP Plus ports on the back of the switch. There are 2 of these ports on each switch, and these are configured as VCPs by default. Simply connecting these together and powering on the switches will form a virtual chassis. The EX2300 platform, however, does not have any VCPs configured by default, and some must be specified if a virtual chassis is to be formed. Only 10 gig uplink ports may be used as VCPs, and these can be configured using the command shown here. This also means if you want to use 10 gig uplink ports as VCPs instead of the QSFP Plus ports on the EX3400 and EX4300, you can simply configure them as VC ports and do so. It's worth noting that the EX4100 platform uses the SFP28 ports on the front of the switch as VC ports by default. This platform does not have QSFP Plus ports on the back. So, we've covered a fair bit about how to configure a dynamic VC. Let's now see about pre-provisioning the VC, as well as a feature called split detection. As we mentioned in a previous slide, we can pre-provision switches in our virtual chassis and specify their member ID by using their serial number. This configuration would be done on the intended primary RE, along with the priority value we saw previously. In this command, we set the member ID and role of the pre-provisioned switch and specify which switch this applies to by using the serial number. When pre-provisioning a VC, the steps are a bit different. We would power on our intended primary RE first, apply the pre-provisioning commands, and then we can power on the remaining switches in any order, since they'll get the appropriate member ID and assume the correct role once added into the VC by the primary RE. A possible situation that can occur is if 2 VC port failures occur, part of the virtual chassis can become isolated from the other part. This can cause significant issues if the switch is performing any Layer 3 functions, as both sections will operate independently with the same configuration. By default, a feature is enabled called split detection that will allow the switch to detect when this situation happens and be able to gracefully merge the two parts of the VC back together once reconnected. However, when operating a virtual chassis with only two member switches, it is recommended to disable split detection, as this can cause issues when one of the switches fails. We disable split detection using the command set virtual chassis no split detection. This will ensure the two switches remain in the correct roles if a split and remerge occurs with a VC with only two members. Great. Let's now review some of the details around managing a virtual chassis. When starting a management session to a virtual chassis, you will always be connected to the primary RE. This is regardless of you plugging into the console port on any of the member switches, or if you SSH into any of the out-of-band management interfaces. Each member switch will run the virtual console process when it is a member of the VC. This will forward any serial console connections to the primary RE that is active at the time. Similarly, all switches will use a VME interface, or Virtual Management Interface, for accessing the out-of-band management interface. All switches in the virtual chassis are managed by a single IP, which is one of the primary features on a VC. This also means that the VC will be accessible and manageable even if the console port and management port on the primary RE are not functional, as long as one of the member switches are connected. Next, we'll review a feature that is very similar to one we've seen before for ensuring minimal traffic disruption during a software upgrade. NSSU, or Non-Stop Software Upgrade, is essentially the same concept and feature as ISSU for redundant RE routers. There are, however, more configuration requirements for NSSU than ISSU. For NSSU to work, the VC must be connected in a ring topology, as opposed to a braided ring topology. Additionally, RE0 and RE1 must be adjacent switches to one another in the VC, and all member line cards must be pre-provisioned instead of dynamically configured. In a two-member VC, the no split detection command must be configured, and all members, of course, must be running the same version of Junos. If you have an inactive switch in the stack because the software version is not the same, then NSSU will not upgrade that switch. Finally, just like ISSU, NSR and GRESS, and optionally NSB, must be configured for NSSU to work. NSSU is performed using this command: request system software nonstop upgrade. Great. Let's move on to the last topic of this lesson: virtual chassis traffic flows. When traffic comes in one line card in the VC and is destined for a port residing on another line card in the VC, it will take the shortest path through the virtual chassis ports to reach the destination. When the VC comes online, a shortest path map, based on the bandwidth of the VC ports and number of hops, is created to help facilitate this. As we see here, if a packet comes in on a member 3 and is destined for a port on member 2, it would traverse the link directly connecting the two, as this is the shortest path between the source and destination. Excellent. I appreciate you sticking with me to review virtual chassis with the EX series Juno switches. I hope that this lesson has been informative for you, and I would like to thank you for viewing.